All right, so we left off here talking about luminosity is equal to the radius squared times temperature to the fourth power. So if you keep the temperature the same and you double the size of the star, 2 radius, that's going to be radius squared, doubling it, 2 squared is 4. You're going to become 4 times as luminous just by doubling the size. It's a fun little thing to do in there. Kind of a question I like to throw at you sometimes too. But anyway, that's a nice equation to know. I forgot to tell you about the third axis. So there's the x-axis, which is the temperature from 30,000 down to 3,000. It goes from hot to cool. So I'm going to do the OBAF-GKM spectral classification. The y-axis is your luminosity, or the brightness in solar units and sun units. And the third axis I forgot to tell you about is the size axis. It's the r circle dot, whatever that symbol is, subscript circle dot, is solar radii. That is the size of our sun, the radius of our sun. So 1 r dot is our sun size. 10 r dot is 10 times the size of our sun. 100 r dot is like Betelgeuse up there, super giant, big. So the diagonal lines on the right side represent size. Our sun is 1 times as bright as itself, so it falls on the 1 y-axis. It is the same size as itself, so it falls on the 1 r dot on the diagonal line, bringing it to about 5,500 Kelvin if you bring that line straight down. So I throw a lot of questions like this at you too, just to extrapolate data from the graph, which isn't that bad. I might ask, how much bigger is Rigel than our sun? You don't see Rigel up there. It's a blue giant, so it's up about above Sirius, above 10,000 luminosity there. So how much bigger? It's at least 10 times plus bigger than our sun. All right, fun little equation out of the book. Question I would normally offer you just have fun with, because it's kind of cool to see this. When I talk about space being space, the average density of interstellar space is 10,000 atoms per cubic meter. That sounds like a lot. But on Earth, our air is 1.7 kilograms per cubic meter. So we're talking atoms to kilograms. So we had to extrapolate that data some. So first of all, we found out a cubic meter contains 10,000 atoms per cubic meter, but we got to multiply that by 1.7 times 10 to the minus 27th kilograms per atom. That means atoms don't weigh a lot. That gets 1.7 times 10 to the minus 21st kilograms per cubic meter to get the density of interstellar matter. So we got them on the same equations there. The Earth is kilograms per cubic meter, space is atoms per cubic meter. So we've done the equation there. It tells us that you need 7 times 10 to the 20th cubic meters of space to be considered equal to the same number of atoms in 1 cubic meter of Earth. That's 20 zeros. That's a lot. I mean, that's more than a million, more than a billion, more than a trillion. That's a lot. It's kind of cool. Anyway, moving on. What is that thing? That thing we call it's an emission nebula. An emission nebula. A nebula is basically from the word nebulous. Nebulous means unclear, fuzzy, cloudy. And that's what a nebulous is. It's just a huge, huge, huge star nursery. It's a big, vast expanse of gas and dust. And emission nebulas they're being lit up, emission, by surrounding stars or stars within them, so they light them up. So a cloud of high temperature gas, which is the atoms are energized and the light and solar winds from the nearby stars or protostars light it up, emitting a radiation. Kind of like fluorescent light bulbs. When you turn on electricity, electrons run through the gas and they fluoresce. So that's an emission nebula. We also have dark nebula. Dark nebula are, again, huge, huge clouds of gas and dust, but they're blocking the light. So they're absorbing the light source from other stars, and they're dark. Here we have the famous Horsehead Nebula. I'd call it the Seahorse Nebula myself, but Horsehead works. All right, this link up here takes you to HR diagrams and discussions from the textbook. So if you want to peek in the textbook and look at some more HR diagrams and how they put them on there, L, big L means luminosity of the sun. In the background, you can see the L. That's how they abbreviate luminosity of the sun. 10 to the minus fourth up to what, 10 to the sixth sun brightnesses. That's a lot. And down below, they put the graph from 40,000 down to 2,500. So it's an all-encompassing graph, temperature Kelvin. So practice, practice, practice. Plot the star groups and label the three axes. So the y-axis is going to be our solar radii, right? I didn't pop that in there. The x-axis down below is going to be our temperature, and the diagonal axis on the right side is going to be our r dot, or the radius of the sun, size of the sun. So blue giants pop up there, red supergiants go there. Where would our white dwarfs go? Right down there. And what's the other one we're missing? The big one, right where our sun belongs to, that big curvy band. What's that called? Main sequence. Good. Where's that go? You got it right there. And then I could throw the brown dwarf, red dwarfs down below. I just don't have room right now. So know what a parsec is. Know how to diagram it and describe it. That's muy importante. Looks like someone did that right here on Paint. Boy, that dude knows how to use Paint. He's awesome. Yeah, I'm not much for big fancy programs, so Paint works for me. Neutron stars. Moving to the next part. A neutron star is not too big, 20 kilometers in diameter. Yeah, that's not too far. How far is that? Well, probably from like your house out to Pacific, Missouri. St. Louis to Pacific. Not too wide, but has the mass about 1.5 times that much massive of our sun. So to put that in another example here, on Earth, 1 teaspoonful of a neutron star would weigh 1 billion tons. Because it's so small and it's high density, the neutron star has been packed in there so tightly that, just like it says neutron, the neutrons are bound together. You know, all that space from learning about atoms in physical science, how you have a big space between electrons and the neutron and proton. Not here. It's been packed in there tight. So the gravitational field is, boy, that's a lot of zeros, 11 zeros times that of Earth. That's not 2 billion, not 2 trillion. That's a lot. That's a lot of zeros. Neutron stars can also have magnetic fields 1 million times stronger than the strongest magnetic fields produced on Earth. Neutron stars are one of the possible ends of a star. They figure they result from the massive stars, which have been huge, and they've undergone their supernova. They've blown up, and the outer layers go off in this huge remnant, and the central region of the star collapses under its own gravity, and it collapses so much because of all the mass, the protons and electrons can combine to form neutrons, hence neutron star. Okay. Hopefully you weren't trying to read along as I said that. You're just listening, and now you can read along. Pause it. Black holes. Just a wee bit to black holes. Black holes are so massive and so intense. They think that X-ray flares are caused by black holes devouring a star. You can click on this video here. Well, you have to go to my notes on my website, open it up and click on it, but it's pretty cool. So you get these jets shooting out. You can see where black holes eating up a star. At the ends, the polar ends, they got these jets of massive energy shooting out. A black hole is so massive that, okay, black holes are so massive that they presume that at the center of every galaxy is a black hole, which the stars orbit around because it's got so much gravity. And a black hole is not necessarily a hole, it's just such a massive amount of mass. The gravity is so strong, the gravity pulls in light. It won't let light escape. So Einstein did his gravitational lensing theory back in the early 1900s that light could be bent by gravity. That wasn't proven until more recently, about 20 years ago, we're looking at two stars, and as a planet came between them, they appeared to come closer together. And as the planet orbited out from between them, they went back to their normal spacing, which meant the planet's gravity pulled that light together, kind of like when you put your finger or something next to some running water, and the water kind of pulls your way by electrostatic mechanisms. Same thing here. The gravity pulls the photons in, so black holes are very massive. Okay, ready to take your test. Review real fast. Giants, white dwarfs, main sequence, supergiants. Yay! Know your Hertzsprung-Russell diagram. Know where they land. This is a nice plotting thing I like to have you do too as an activity. Plot the stars. Here's the Harvard spectral sequence. Again, you see the OBAF GKM. You see the temperature. You see some examples over there. Just nice to know. Luminosity versus temperature. Yes. Hertzsprung-Russell diagram reminds you that just because it's hotter doesn't mean it's brighter. You could have a hot white dwarf that's not as bright as Betelgeuse, a cooler star, but much bigger. Because remember, radius squared times temperature to the fourth is what makes it luminous. And here's a nice little plot for you, again, to visualize it. I can't emphasize enough how this will help you understand this. So go back, look at them over and over again. And that ends our final unit of astronomy for notes.